Today we're going to talk about collisions, and I'm going to show you what happens when this massive car of 3 kilograms runs into this red car of 1 kilogram that's originally at rest. Let's watch them hit. So the one moving at 10 meters per second to the left has a negative 10 velocity. The one that started off at rest, the red car, started off with a velocity of 0. And what you're going to notice as a result of the collision is that each car changes their velocity. And so you see that the blue car has slowed down and the red car has sped up. And what we're going to do is try to analyze the impulse and the change in momentum of each car. So what I have for you in the notes would just be a screenshot of the initial conditions here. And what we're going to see is the red car and the blue car running into each other. And what I want to draw is the point of contact when the red car and the blue car hit. Remember, the blue car had the mass of 3 kilograms and the red car had the mass of 1 kilogram. When they hit each other, the blue car pushes the red car to the left. That is going to be represented by an arrow. That arrow shows the force of the blue car pushing on the red car. Then the red car pushes the blue car back to the right. We know, due to Newton's third law, that these forces are equal in size and opposite in direction. So the force that the red car gives the blue car has to be equal to the size that the blue car gives the red car. Remember, that's Newton's third law of action, reaction. And that says that the forces are equal in size and opposite in direction. So I know that the red car can't give a force any bigger than the blue car, that the force from the red car is always going to be equal in size and opposite in direction to the force from the blue car. Also, during a collision, that force acts over a certain amount of time. And what we want to do is talk about the collision time. When we talk about collision time, we're talking about the time of contact between the two cars. And so the idea is the red car can't be in contact any longer with the blue car than the blue car is with the red car. That time of contact is always equal as well. I can't touch something for longer than it touches me back. So those two things are going to be the same during a collision. The forces have to be the same, and the times that those forces are acting have to be the same. And we know that force times time is actually equal to an impulse. So impulse is found by taking your force times your time. It turns out that the impulse that the blue car receives is equal in size but opposite in direction to the impulse that the red car receives. Doesn't matter the size, it doesn't matter the speed. During all collisions, each object always receives equal impulses. I can't give you a bigger impulse than you give me back. It's impossible due to Newton's third law. We also know that there's that theory of impulse and momentum, that whatever impulse you receive causes and is equal to your change in momentum. What that means is however much the change in momentum was for the blue car, it has to be equal in size but opposite in direction to the change in momentum of the red car. This is again true in all collisions. Anytime two things hit against each other, we're going to always have equal forces, equal times, equal impulses, and also each object will change momentum by the same amount. Doesn't matter the size of the car, it doesn't matter the shape of the car, it doesn't matter how fast the car is going, that when two things collide, they are always going to receive equal forces, equal times, equal impulses, and equal changes in momentum. It seems as though everything is equal, but what we notice here is that originally this car is moving at 10 meters per second. That's the initial velocity of the blue car, negative 10 meters per second. And initially, the velocity of the red car is 0 meters per second. And what we see is that the final velocity of the blue car is negative 5 meters per second. And the final velocity of the red car is negative 15 meters per second. Remember that to find our change in velocity, we're going to be doing our final velocity minus our initial velocity. So if we're looking at the change in velocity of the red car, we're going to take its final velocity minus its original velocity, and we're going to see a change in velocity of the red car of negative 15 meters per second. If we're looking at the change in velocity of the blue car, the change in velocity of the blue car is going to be the final velocity, that was negative 5, minus the initial velocity, which was negative 10. So negative 5 plus negative 10, or minus negative 10, is the same thing as adding them together. And the change in velocity of this one is actually going to be positive 5 meters per second. These objects, even though they had the same force, the same impulse, the same change in momentum, and when I say same, I mean the same magnitude change in momentum, they experienced different changes in velocity. So why, for the same force, would we receive different changes in velocity? Oh yeah, inertia. The one with more inertia had a smaller change in velocity, and the one with less inertia received a bigger change in velocity. And so what we're saying is that because these two momentums had to be equal in size but opposite in direction, the change in momentum of the red car was equal in size, opposite in direction to the change in momentum of the blue car. But remember, change in momentum is mass times change in velocity. And so really, it's not that their changes in velocity have to be the same. It's that their product, when you multiply those together, it has to be the same. So it turns out the one with the smaller mass has a bigger change in velocity. And the one with the bigger mass has the smaller change in velocity every single time during a collision. And so one of them changes their direction one way, one of them changes the other, but the idea is during all collisions we have equal forces, equal impulses, equal changes in momentum, but our change in velocity depends on our mass. Big masses don't have to change their velocities by very much. Small masses need to change their velocities a lot in order for those changes in momentum to have the same magnitude. Have a great day.